I am Mr. Ish and I welcome everyone to this video where we are examining projectile motion. The maximum range of the projectile motion, how far did that projectile go? What are we looking at? If you have here your ground level, you're shooting a certain projectile at a given angle with a given initial velocity which is not equal to 0 because you want a motion to occur. Your projectile will go in a parabolic manner and it will land somewhere right here. What is this distance, your displacement? Why am I calling it Sx? Because you're looking at something here, displacement along your horizontal component, your x-axis, Sx. That's what we're trying to do, determine this. Look here at your velocity. If you look at your velocity, it represents a hypotenuse of a certain triangle, and that right there is your velocity. You have here a right triangle, a certain angle here which is equal to your angle at which the projectile is shot with reference to your horizontal, your ground. You can easily determine your horizontal component and your vertical component using trigonometry. Cosine of this angle is equal to adjacent or your hypotenuse, which means your x component, your velocity, is equal to what? It's equal to v naught, your initial velocity, times cosine theta. And I'll put that right here. Your x component of your initial velocity is equal to your initial velocity times cosine theta. Likewise, your y component is equal to initial velocity times sine theta. And you'll see it come out right over here. You do sine theta is equal to opposite, which is your y component of your initial velocity or hypotenuse. You solve for it and you take it and you have it. I've given you two equations. They help you get to where you need to be, but you're not there just yet. And now we have to do something with these. Look, we're looking here at the maximum range of your projectile, your Sx. If you think about here, one of your laws of motion, there's a displacement equation which is equal to what? Initial velocity times time plus half at squared. You're looking here at a certain x component and a y component. How can we figure this out? If you look here at your x component of your displacement, gravity does not factor in because you're looking along the horizontal axis. You're going to bring in a substitution for initial velocity, which will be right here, your x component, because you're looking at that. You will have here initial velocity times cosine theta times time. That'll give you your displacement along your x-axis. If you want to do your y-axis, it's easy. Your displacement along the y. You just bring in your items. What are your items? You know your acceleration, which here a is synonymous to gravity, is going to be opposite to your velocity vector. Then you're going to bring in your substitution. You have v initial velocity times time. You're going to bring in this initial velocity times sine, because that represents your velocity along your vertical y-axis, times time minus half at squared. Remember, in all instances, a can be substituted for g. These are your two equations. Well, what's your relevant equation? It's this. This right here represents one of your equations. I want to determine the maximum range of a projectile shot at a given angle, and I have two ways of doing it. One way is this. I'll put this equation here. Your displacement, your maximum range, is equal to initial velocity and the cosine of that angle times time. That's one equation. But there's another equation. But notice, this equation requires you to determine time. Sometimes you don't have that information given, but there's another route. What is that other route? Now you look here at this particular equation, there's something you can do with it. You can solve for time. I'm looking right over here. I have a quadratic equation. I can solve for time. I have a initial velocity sine theta times time minus half at squared. I can factor out time because it's a common variable. All of this is equal to 0. If I were to factor out time, I have a VO, your initial velocity, sine theta minus half at. All of this is equal to 0. When I solve for time, I have two factors. One this factor, one this. T is equal to 0, but I'm not interested in that because that represents the start of the experiment. No motion has occurred. I'm interested in the time coming from right here. Push everything on the other side and solve for t. I would have your t is equal to what? Minus initial velocity times sine theta divided by minus a, and you're going to push the denominator 2 on the other side and multiply. You can cancel these out and you'll have your 2 times initial velocity times sine theta over acceleration, and this right here is equal to t. What will you do with this? You can bring it right over here, the substitution for it. I'm giving you two equations here. One is your easy equation, but it requires you to know time. The other equation will eliminate the time variable, but it'll bring in the acceleration, and I'll show you what I mean. Your other equation will bring it in over here. Let's erase this. We don't need to see this anymore. You're going to have over here Sx is equal to v naught cosine theta times time. You bring that over here, 2 initial velocity sine theta over a. Simplify this or bring things together. I will have here a 2 I have here a initial velocity squared. I have sine theta, cosine theta, all over acceleration. But you can simplify this. Look, 2 sine theta cosine theta is no different than sine 2 theta. And then I have this initial velocity squared over a. Here's your other equation. You have 2 equations which can give you your maximum range of projectile. One is this. It's relatively easy and it's direct to come at. It's easily derived, but you need the time. This other equation is this. Initial velocity squared times sine of 2 theta over a constant, which is your acceleration or your gravity, but there's no need to know time. You don't need to know it. And it's good. Time variable has been removed. You could easily reconcile everything I'm showing you here, and I will before I put these things into effect. I've given you 2 equations to determine the maximum range of a projectile, which is how far the projectile went. Where was it when it landed with respect to where it was started? You have 2 equations. Yeah, one is initial velocity times cosine theta times time. These are all in a product relationship is equal to your other one, which is right here. Your initial velocity squared, you have a sine 2 theta and over acceleration. In this equation, you need to have the initial velocity, you need to have the time and the angle, and you can easily determine how far the projectile went. In this equation, you need to have the initial velocity, you need to have an angle, and you need to know the acceleration, but that's easy, that's a constant. How can you reconcile these? Solve for t. If I were to reconcile it, I know this right here can cancel out with one of these exponents and it'll go away. I can open this up. I have here cosine theta and a t is equal to what? I have 2 times VO sine theta cosine theta. This is me opening up my this via double angle formula over a. I have a cosine theta, it will cancel out with this. And now I'm looking at t is equal to what? 2 v naught, your initial velocity, times sine theta over a. Now we've developed yet another equation. If you wanted to go by this route here, the very top equation, where the displacement, the maximum range of your projectile, how far it went, is equal to initial velocity times cosine theta times time, but you don't know the value of time, I've given you the equation. To determine the time of the projectile's travel, how long was it that it traveled before it landed, it's equal to 2 times your initial velocity times sine theta divided by acceleration. Then here's another equation. It reconciles this with that. It's easy. Now let's put everything here into perspective so we can close the video with a good example. What is my good example? I have a projectile which has been shot at an initial velocity, let's say, of 70 meters per second. It has been shot at an angle of, let's say, 70 degrees. We don't know the time, but we can easily determine it. We need to determine how far it went. What is the maximum displacement? We can do it. Let's use this second equation because you don't need to know the time and you can arrive at your Sx. I'm looking at the second equation, which is this. Initial velocity squared times sine of 2 theta divided by acceleration. You know acceleration is 9.8 meters per second squared. Let's plug it in. I have here 70, 2 times that theta is 140. I'll do 140, the sine of that, times my this initial velocity squared times 70 square divided by 9.8 meters per second square. I'm getting here 321.39. I'll round it up to 321.4 meters. My projectile traveled a distance of 321.4 meters to the right. If here's your starting point at rest, it went 321.4 meters to the right and it landed at an angle of 70 degrees with an initial velocity of 70 meters per second. This was me using this equation. Now let's use this equation, but this equation requires you to have time, but now you have an equation for time. Time here is equal to 2 times your initial velocity. What is that? 70 times sine of what? You'll do sine of 70 divided by 9.8. Let's determine the time and we'll do it. We have 70 sine times 70, which is your initial velocity, times 2 divided by 9.8. And now I'm getting here 13.424 seconds. Let's put it down. 13.424 seconds. What does this mean? It means that the total travel time, how long your projectile stayed in the air during the motion, was 13.424 seconds before it landed. And now we'll use the second equation. We know the second equation is equal to your initial velocity times cosine theta times time, and you just plug in your items. I have my time now. It's 13.424 times cosine of what? 70, cosine it, times my initial velocity 70, and we'll have 321.38. I'll round it up to 321.4 and it will be correct. When you're looking here at projectile motion where an object is shot at a particular angle with respect to your horizontal, which is your ground, graphically it's your x-axis, at a given angle where the initial velocity must not be equal to 0, otherwise you have no projectile motion to analyze. Acceleration and gravity are interchangeable. You have two equations for the maximum range, how far that projectile went. Initial velocity times cosine of a given angle, which you know, times a time. This top equation requires you to know three items: initial velocity, your angle, and your time. Then you have another equation, initial velocity squared times sine of 2 theta over acceleration. Here you have to know two items, your initial velocity and your angle. This acceleration is constant, you don't have to worry about it, but you have two routes. I've shown you the time can be determined by this, 2 times initial velocity times sine theta over your acceleration, and it's your reconciling factor between these two. If you were to plug this item here for time right over here, it will convert this equation into this equation if you were to simplify it, and it would be indeed correct. We've done here derivation for you, we've done example for you, two routes. The answers are good. This answer, time of distance in travel, is good. Your total displacement to the right, your maximum range is good. Thank you for watching.